All right, welcome back, ladies and gentlemen. Let's get rolling here. We're going to go ahead and go through homework number 2, question by question. Again, something to keep in mind in this first question is that we are not writing a proof. We are not writing a proof. We are not writing a proof. Instead, we are simply justifying our steps. Like, if you were to create this stuff we've been doing with proofs, um, we are simply trying to say, well, if this was like the last step, how to justify this last step. And I think there might be confusion on the previous worksheet because it was linear pairs, and I discussed that, and it was actually going to be like definition supplementary that gave us the equation. And sometimes that's going to be a little confusing, but just try to keep in mind like this is like almost like one module within a bigger proof. This is not proof. So please keep that in mind. Anyway, so for this first question, what are we dealing with? Well, we're trying to get excuse me trying to find the values of the unknowns. We simply have these three statements to work with, or with which to work. So we might have to take a second and figure out where these things are. JLC 3x plus 45 degrees. So 3x plus 45. Ooh, it's green. Look at that. CLF is going to be 2x plus 50 degrees. And we're told JLF, which would be JLF, that's the entire angle, ladies and gentlemen. That's going to be 170 degrees. So it seems to me we're dealing with angle addition postulate, meaning that if I take two smaller angles and I add them together, I have the value of the entire angle. Pretty mind blowing, right? So that's how we're going to set this up. So we have 3x plus 45, which is JLC, the first angle, and we're going to add 2x plus 50, the second angle, CLF, and that should be the value of the entire angle, 170 degrees, JLF. And again, this is going to be angle addition postulate for a justification. That's how we're actually doing it. Now, before you guys start complaining, are there other things in here too? Yeah, absolutely. You know what? There's going to be a little bit of substitution um, along with our angle addition postulate. But again, we're not writing a proof here. We're simply pointing out like the big idea, the big postulate that allowed this to happen. Substitution is kind of a minor thing in compared to say like an angle addition postulate. Now we're just into the solving steps. Here we have 3x, 2x, that's going to give us a 5x. 45 plus 50 should be 95. That's equal to 170 degrees. Let's go ahead and subtract off our 95 from both sides. So it'll be a 170 minus 95. That's going to give us 75. So 5x is 75. And therefore, after we divide by 5, that's going to be, x is going to be 15. Okay? So again, angle addition postulate's a big idea here that you use. Are there minor ideas? Absolutely. There's substitution involved along with solving. But again, we're not writing a proof. We're just trying to get a value. In the end, x equals 15. That's what we're trying to search for. And moving on. Okay. So again, we're finding the values and unknowns. We have this kind of crazy diagram. We have things in the diagram that we are told. So step one, absolutely, is get that stuff in the diagram. MJ and CF are the same. So let's kind of map that out. So MJ, this distance right here, is the same exact distance as CF. That's pretty important, I think. I mean, I don't know how it's going to be used, but it's definitely in our givens. We'll probably use it. MC is 3x plus 10, so I'm just going to write in here 3x plus 10. CJ in the middle is going to be 2x minus 2. Um, and then JF over here will be 6x minus 20. All right, so what do we do? Well, we need an equation, right? So if we're going to solve this thing, like we're going to actually have to write an equation, substitute values in it, and then manage to solve. Well, the only thing I think we have to go on is this idea. MJ is congruent to CF. Well, if this section is congruent to this section, that's an equality, guys. That's definition of equality. So MJ segment being congruent to CF segment is the same thing as saying MJ measurement is equal to CF measurement. And that's going to be definition of congruency, which I'll just abbreviate def of congruency. Now from here we have our equation. It becomes substitution solve time, guys. MJ is made of two parts, 3x plus 10 and 2x minus 2. So MJ would actually, using a little angle or segment addition postulate, excuse me, should be 3x plus 10 plus 2x minus 2. And that should be equal to CF, which again, using a little segment addition postulate, should be both 2x minus 2 plus 6x minus 20. So we have 2x minus 2 plus 6x minus 20. Now from here is pure on algebra, guys. So we just have to solve for x. But here's the observation you should make right off the bat. If 2x plus 2 is on both sides of the equation, they essentially cancel themselves out. I mean, think about it. Like, if we're going to take 2x and subtract it from both sides, minus 2x, boom, they're gone. If we're going to add 2x to both sides, plus 2x, boom, they're gone. That's just a straight up cancel. So really we just have to solve 3x plus 10 is equal to 6x minus 20. Which again, should be kind of trivial, right? So let's subtract 3x to this side. Let's add 20 to this side. So that's going to be 30 is equal to 3x. X shares a value of 10. And happy face, because we got it right. Maybe put some ears on there and some hair. All right. So x equals 10 is the solution. So let's move on. Okay, find the length of the segment with a given endpoints. Now, guys, this is actually going to be just reinforced practice, what we did literally today. Now, you could have drawn a graph. You could simply do some counting. But I'm going to go ahead and use a distance formula because you know what? Why not use a distance formula? So if the distance between two endpoints, like the distance of AB, is given to be the absolute value of x1 minus x2 squared plus y1 minus y2 squared. I just had to do a little plugging and chugging here. I probably want to take a moment and identify what my x1, x2, y1, and y2 are. And honestly, guys, as we talked about in class, it doesn't matter. Let's make that the x1, making that the x2. Let's make that the y1, making that the y2. So now let's go ahead and input these pieces into our diagram, or excuse me, our formula, and go about our merry. So x1 here, x2 there, y1 here, y2 there. So rewriting my equation now with inputted values, I should have x1 being 4, subtract off x2 also being 4. Well, that's going to be convenient, squared. And then y1 being 1, and y2, ooh, back that up. Okay, so y1 being 1 and y2 being 9 squared. And now let's do some solving. 4 minus 4 is 0. That's done. I don't need to worry about that because if I add 0, nothing actually changes. 1 minus 1, ooh, excuse me, 1 minus 9 is negative 8. Square that, you'll get a 64. Square root of 64 is both the positive and negative 8, but we don't consider the negative case. It's a distance. So we're just left with a distance of 8. Now you may be saying, Mr. Collins, could I just have counted that or just use logic, like looking where those points are and maybe graphing them? Yeah, that's pretty cool. We could do that. Like this was a vertical segment, so I mean, yeah, all those techniques have been great. But since I have the distance formula, I know it works every time. Why not use it? We're going to go ahead and skip the next question because, as someone pointed out, it's actually the same exact question. That's a copy and paste error. So we're just going to go ahead and skip down to number 5. Okay, so it's been stated that 4 points are needed to define 3D space, but not just any 4 points. Describe the orientation of the points necessary to find 3 dimensions. Okay, so guys, here's the deal. Simply choosing 4 points does not guarantee a 3D space. Allow me to demonstrate. So if I just had this plane, and I chose point 1, point 2, point 3, point 4, I'm still only defining 2 dimensions. Like I don't have that dimension of height popping off this plane. Or, for example, what if I chose 4 points, but they all happen to be collinear? 1, 2, 3, 4, all in one line. There's 4 points, but they're collinear. That's not a third dimension. It's not even a second dimension, guys. So when you say choosing the points of the orientation, we're looking for a key word or key phrase. Either way, we're describing an idea. We know that if I choose any 3 points, say point 1, point 2, and point 3, then without hesitation, I know those are going to form a plane. We talked about that extensively. So 3 points, we have no choice. We'll form a plane. It's the 4th point we got to be careful of. If I choose that next point to actually be on the plane, like if I choose it to be like right here, that's no good. I have to choose it to be non-coplanar. Non-coplanar. Okay? That's a key phrase I'm looking for this 4th point. So if I choose, in other words, to be like above the plane or perhaps below the plane, now I'm in business. Now I actually have a 3rd dimension. Because if I have a 3rd point off the plane, then using that point and any 2 points already on the plane, I have a new plane. So here's 1, 2, 3 for that plane. And let me switch colors here. we're using this point, and let's say this guy and this guy, 1, 2, 3 for a new plane, and then maybe going to the back of this, we're using the same point but now utilizing these two, 1, 2, 3 points that are playing. Guys, that's 3 dimensions. That's multiple planes. That's 3 dimensions. It has length, it has width, and it has height coming off the page. So the 3 points, the 4 points, have to be defined to be non-coplanar. If you do that, you're guaranteed 3 dimensions. Last question of this set. Explain why the procedure below would not produce a correct angle bisection. Well, let's kind of think about what they did. Um, they used an assumption that we were trying to gently stop you guys from making, which was simply finding 2 circles who were centered on these endpoints. So if I took this circle, oh look at that, it matched up perfectly, and I would take this circle here, oh look, it matched up perfectly. That's the intersection of circles, but guys, these points are not equally spaced. This would not produce an angle bisection because the centers of these circles are not the same distance back to this point here. Like this distance and this distance are not the same. That's essential because all you're really doing here is really bisecting this line. If this line that I just drew is not bisected, then this angle is not bisected. So we're actually using the same technique as bisecting a segment, but we're applying it and we're kind of showing how it's going to also, as a result, bisect this angle. So the fix of this is actually pretty simple. I have to shapes circle. I have to choose. Excuse me. I have to choose starting points for my circles that are the same distance apart. Hence, they have to start in the same circle. So if I use this point to generate one of my circles, and I use this point to generate the other, okay, where they intersect should be my angle bisector. Now, forgive me because I am doing a little bit of estimation here, but I'm just trying to demonstrate a point and not actually create a bisection. So the whole kind of crux of this situation is choosing 2 starting points for your arcs that are the same distance from a starting point. And that's why it didn't work this time. Okay? So guys, I hope that helped. Again, rewatch this as many times as necessary. Watch it at home if you need to. Certainly, if you need questions, raise your hand. I'll get to you as soon as I can. But there you have it. That's worksheet number 2. And the stop button.